Hi, folks. So it's time to start into a new topic and a very interesting one at that. What we're going to talk about now is repeated games, and so this will use some of the reasoning we've had in terms of subgame perfection and extensive forms. But now think of situations where players are playing a game, but they're playing it repeatedly over time. So, when we think of most interactions in the world, there's a lot of them which occur more than once. So, when we think about different kinds of things, firms in a marketplace, they're interacting with their competitors. They're doing it day after day after day. We think about political alliances, countries deciding how they should negotiate with other ones, whether they should have conflicts and so forth. Those are things where this happens repeatedly over time. So there's a long history and a long future ahead of them. Friends, do you help your friends out when they need help? Do they help you back when you need it? So you're going through repeated interactions and how you've performed in the past. If you have friends that have done very well for you, you're more likely to reciprocate. Some of these kinds of things can involve repeated interactions. Workers, team production. You've got to, day after day, you need to help some of your coworkers. Sometimes you have to do tasks that don't go noticed, and sometimes they do help you out, and so forth. So these are situations where repetition can make a difference, and understanding it will be an important aspect of understanding how the repetition affects the play. Involves a whole series of different kinds of things. Just to fix ideas, let's talk a little bit about OPEC. Which was a cartel which was formed in the early 1970s. And just in terms of background, if you go back to the period between 1930 and up to 1973 when OPEC started being put together, the price of oil, so these are all adjusted numbers to reflect, say, 2008 dollars, so we adjust for inflation and other kinds of things. But if you adjust everything to the same to adjust for inflation, you get a price of roughly $20 per barrel or less from the period of 1930 through about 1973. OPEC starts to form, and what happens? They decide that they've just been acting. It's a bunch of players, a bunch of different producers. They've been acting on their own for many years, and just pumping lots of oil. And they pump so much oil that the price is fairly low. It's very easy to buy oil. So they're going to start by restricting production, cut production back down, and that'll drive the price up. Okay. What's the difficulty is if all the other ones are producing very little and driving the price up, I'd like to cheat on the agreement and pump more oil. So you can think of this as looking somewhat like a giant prisoner's dilemma game, where we'd all like to pump less oil if we're OPEC or oil-producing countries, drive the price up, but we all have an incentive to cheat a little bit and pump more oil. And the repetition can help us police that if we're OPEC. So what happens? By 1976, the price goes up to about $50 a barrel. By the time you get to 1982, these are all also in real terms. So these are adjusted for inflation. They've pumped the price up to $90 a barrel. And, so in the early 1980s, it does quite well in terms of OPEC, lots of money coming in. And then it collapses for a while. So when you look at the period, say, between about 1986 to 2002, so between 82 and 86, it starts to erode. It kind of falls apart. Between 86 and 2002, the price is basically $40 a barrel or less. And then they get back together again. So actually, during this period, there was the Iran-Iraq war, a whole series of things go on in the Middle East that make it much more difficult to sustain cooperation. Things deteriorate, and then after a while, things are getting back in terms of higher prices. By late 2008, the price is pushed back up to over $100 a barrel. Okay, so what we need to begin to understand this, understanding the repeated interaction and understanding the motivations of the players and so forth can help us quite a bit. So when we think about this, a cartel is much like a repeated prisoner's dilemma. And in order to make sure that other people behave, if you want to get people abiding by this, you need to be able to observe other people's play and react quickly to that and punish undesired behavior. So if you form a cartel and say, everybody, here's our quotas, don't pump more than this, you need to be able to respond to somebody who ends up breaking their agreement and pumping too much. So you need to be able to observe what's going on. You also need to care about the future, right? So If you stop caring about the future and only care about today, then it's very tempting for one of these countries just to say, okay, forget the agreement. I'm just pumping as much as I can today. The price is very high. I'm going to grab what I can. And wars certainly didn't help this, right? So if you have a war, you need cash up front. You're going to want to pump much more oil, and that makes it much more difficult to abide by the cartel agreement. You also need a stable set of players and stationarity. So the more complicated the setting becomes and the more sources of oil there are in the world and so forth. So constantly changing sources of production can hurt. Growing demand can help, actually, right? So if the world is getting more and more oil dependent and countries come online that have more and more demand for oil, that can help drive the price up. So in understanding repeated games, we'll have to account for a lot of things over time. But we can begin to analyze this using the tools of game theory and looking at situations where people are playing games, but they're playing them over and over and over again, and trying to understand the consequences of that. How does threats of future play impact play today? So that's the basic idea, and let's get into that in a little bit more detail.
In this video, we're going to look at how to define utility in infinitely repeated games. So remember that the way that an infinitely repeated game works is that we have some stage game, which is a normal form game, and the players repeatedly play this same game over and over again. And what that means is each player gets a sequence of payoffs. Let's say player I gets the sequence R1 in the first repetition, R2 in the second repetition, R3, just on and on infinitely. So we have this infinite sequence of real values, which are the payoffs that this player has gotten. But if we want to reason about this game, we can't really reason using utility theory about an infinite sequence. We instead have to take this sequence and turn it into a single number that talks about the utility that the player has for having played this sequence. And so how do we do that? What's the right way of thinking about that? So the first thing to notice is that previous things that we've learned about game theory aren't going to be sufficient to answer this question. So you might wonder if we can take this infinitely repeated game and just write it in extensive form. And of course we can't. And the reason is that the extensive form would be infinitely deep. We would never get to a leaf node where we could write a payoff. And so that won't help us. You might also just wonder, can we sum up this sequence of payoffs and just say that my utility is the sum of these values? And the problem is that that sum can be unbounded, because if, for example, every payoff I get is positive, then I'm going to have some unbounded amount of utility at the end, and so that's not going to work for me. I want to have finite utilities. So instead, there are two canonical ways that this gets defined, and I'll tell you about both of them in this video. So here's the first one. So the first thing says, let me look intuitively at my average payoff over this sequence. Now, the average payoff of a sequence is also not well defined because, of course, the way I take an average is I sum everything up and then I divide it by the number of things. And we've already seen that the sum can be unbounded. The number of things is unbounded as well. So I would have infinity divided by infinity, which wouldn't help me out here. But what I can do instead is to look at the limit of finite averages as the averages get longer and longer. So what I can say is, let me look at an average over the first k things in my sequence. And then let me take the limit of this average as k goes to infinity. And it turns out, actually, technically, this isn't always well-defined. It's almost always well-defined. And there's an easy fix that we can do to this definition that I've left out here to keep it from getting too technical. But in cases where this is well-defined, this is the right thing to do. So, and everything we'll talk about in this course, it'll be well-defined. So this is defined as the average reward that the player gets over the infinite sequence. So this gives us one number. The reason we have a second definition is that there's something kind of counterintuitive about the average reward. Let me put it back up. The reason that it's kind of counterintuitive is that if I get some bad payoff for a finite amount of time, let's say for the first 100,000 iterations, I get a payoff of -1 million. And then for the rest of time after that, I get some good payoff, let's say 1 unit of utility. Then the limit of the means would be 1, because the negative payoff that I got at the beginning was only for a finite amount of time, and it washes out in the average if I go long enough out into the future. And Well, that's what the math says, but that doesn't always model what we want to really reason about, because we have an intuition that payoffs that you get early on are kind of more important than payoffs that you get really far into the future. So if we want to have a model of utility that has that property, we need to say that different payoffs matter differently. So it's more important to me to get a good payoff in the first iteration than to get one in the millionth iteration. And the way that I can model that is by saying my payoffs are multiplied by some discount factor. So my discount factor talks about my value for payoffs at different times. So my discount factor beta is some value strictly between 0 and 1. And you can sort of think of it like an interest rate. It's saying, with money, if I wanted to tell somebody that I'm going to pay them $100 in a year, they would value that at less than $100 today. And the amount by which they would value it less today kind of corresponds to the interest rate. And that's kind of exactly what's going on in the math here. So what I'm saying here is that my utility for this stream of payoffs, this stream of R's, the stream of payoffs, is weighted by the discount factor to the power of which payoff in the sequence it is. So I'm going to discount each payoff successively. So the first one is going to have the discount factor applied once. The second one is going to have the discount factor applied twice. So I'm going to get the discount factor squared, and so on, all the way through the sequence. So each of them is going to be diminished, but each of them is still going to matter. And there are two ways we can think about what the discount factor means. So the first is kind of the interpretation that I've been telling you so far, that the agent just cares more about the near term than the long term. There's another definition which is different but mathematically the same, so it's interesting to think about. And that is that the agent really is the agent we just talked about in the average reward case, cares just as much about every payoff. But with some probability, the probability actually 1 minus beta, the game will end in every given round. So our game is not necessarily infinitely repeated. It's sort of potentially infinitely repeated. But every time we play the game, we're going to flip a coin. And with probability 1 minus beta, the game is going to just end. And with probability beta, the game is going to continue. And what that means is that here we'd be talking about my expected reward in the game, because there's a beta chance that I'll go to the next round. There's a beta squared chance that I'm going to go 2 rounds forward. There's a beta cubed chance I'm going to go 3 rounds forward, and so on. So that means my expected utility in this game would just be the same formula. And that's it for defining utility in these games. Thanks very much.
Let's now speak briefly about stochastic games. This is a topic that lends itself to a very long discussion and quite a complicated one, but we'll touch on the main points and position it in the landscape of topics we're discussing. And so the starting point are repeated games. As we know, a repeated game is simply a game in normal form, for example, that we repeat over and over again. For example, we play Prisoner's Dilemma once, twice, 3 times, maybe a finite time, maybe an infinite number of times, and we accumulate all the rewards all the time to some overall rewards. A stochastic game is a generalization of it, where we play games repeatedly, but not necessarily the same game. So we play a game. Depending on how we played that game, let's say Prisoner's Dilemma, we each got some payoff. But depending on how we play the game, we also probabilistically transition to some other game, play that in turn, and the process continues. A graphical way to look at it is here. If this here is a repeated game where you play the same game over and over again, here you play the game, and then if you happen to play this, you'll transition to this game. If you happen to play this, you'll maybe transition to the same game. If you play this, you'll transition here. If you play this, maybe you'll play this game again. And so on. From each game, you transition probabilistically to other games. This is a stochastic game. Formally speaking, it's the following tuple. It's a lot of notation, but the concept is exactly what we saw. We have a finite set of states Q, we have a set of players, we have a set of actions where actions are available to specific players. So A sub I is the action available to player I. And then we have two functions. We have the transition probability function, so depending on the state we're in and on the actions we took, we move to each of any of the other states, or the very same state, with a certain probability as governed by this probability distribution. And similarly, reward is the reward function, which tells us if in a certain state a certain action profile was taken by the agents, then this is a reward to that particular agent, to each of the agents. So R sub I is a reward to agent I. That's the formal definition. Notice that it sort of assumes implicitly that you have the same action spaces here, but you could define it otherwise. It simply would involve more notations and nothing inherently important about the action spaces being the same in the different games within the stochastic game. So just a few final comments on it. First of all, as we saw, this obviously generalizes the notion of a repeated game, but it also generalizes the notion of an MDP, or a Markov decision process. If a repeated game is a stochastic game with only one game, a Markov decision process, or an MDP, is a game with only one player. And so you have states there where the agent takes an action, receives a immediate reward, and probabilistically moves to some other state. And the only difference is that he's the only actor in the setting. I mention this because MDPs have been studied substantially in a variety of disciplines, from optimization to computer science to pure math and beyond. But also these two perspectives of a generalization of repeated games and of MDPs give you a sense for the theory and investigations into stochastic games. So from repeated games, we inherit the definitions of different ways of aggregating rewards over time. You can have limited average rewards, future discounted rewards. Whereas from the literature on optimization and on MDPs, we get notions such as stationarity and Markovian strategies. These have to do with, we also have notions of reachability, about the structure of the underlying transition probability. And so again, these are issues that are involved that we won't get into more in this lecture, but at least we flagged their existence.